the problem description, we are given an arbitrary array. Okay? Yeah. Because we do not mention ordered or unordered, that means it's unordered. Okay? If we do not say ordered, unordered, that means unordered. Yeah. And it could be ordered, but that's a special input. Yeah. Because sometimes I ask you when the input is ordered, so it could be ordered. Yeah. But we treat that ordered case as a special input. Yeah. All right. The question, how to check if all the elements are distinct. Yeah. And last time, remember at the end of the class, near the end of class, I talk about a problem solving commonly used method. Yeah. Let me repeat. Last few sentences I talked about before the end of the class. Yeah. So in problem solving, we know to solve a computing problem that is not very easy. Yeah. That is not very easy. Yeah. Usually it is based on the understanding of the problem. Yeah. If you understand the problem well, okay, understand from all aspects. Yeah. Yeah. Some students, you may ask, what should we do when we try to understand the problem, right? You need to do something, right? Yeah. You make your observations. Yeah. From, various angles, and try to find some properties. Yeah. So when you do your understanding, you try to find special properties in this problem. Yeah. So that's typically what you do. Yeah. Yeah. The more properties you can observe, yeah, the better, because in your problem solving, you may need to use some of the properties. Yeah. Yeah. All right. But at the beginning, usually people do not understand the problem well. Okay. At the beginning. Yeah. Yeah. So you need to build up some experience. Yeah. So you need to, put your hands on, right? Yeah, you need to do some work, yeah, to collect some experience, yeah, to help you understand the problem better. Yeah. But how do you do something, right? How do you do something? Yeah. So because at the beginning, when we do not understand problem well, we cannot find some advanced algorithm, right? Yeah, because it's very hard to develop some advanced algorithm to solve the problem. So at the beginning, most of the time, what people can do, apply the brute force method to solve the problem. Brute force method. Yeah. We know we do not expect good solutions from the brute force method. Yeah. So most of the time, the brute force method cannot give you a good solution. Yeah. Very slow. Yeah. But at least it helps us to collect some experience. It helps us to understand the problem better. Yeah. Yeah. All right. So the first method, let's try the brute force method to solve this problem. Okay. Yeah. 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 All right. At the same time, we can understand the brute force method better. Yeah. All right. When we do the brute force method here, we do nothing to organize data. Yeah. We just work on the problem directly without any preparation. Yeah. Just do it. Okay? Yeah. Just, do the work directly. Do the comparison work directly. Evan is here. Okay. Yeah. The brute force method. All right. Yeah. Okay. Yeah. So, but in general, we know in problem solving, many times people need to, before they work on the solutions, they need to spend some time to organize data. Yeah. Because if you can organize data with some special structures, you can take advantage of the structures to make your overall efficiency better. Yeah. So that's the usual way. Yeah. But here, because in our mind, we just want to use the brute force method. Yeah. So we don't want to do anything to organize the data. So in this step, there is no cost. Okay. We save the cost. Okay. Yeah. But because because the cost you spend here, we treat it as investment. Yeah. Because later we will enjoy the work we invest here. Yeah. But here, no cost, no investment. So then we do everything from scratch. Okay. Yeah. All right. Let me draw a diagram. Yeah. All right. Yeah. So in this diagram, so we can imagine we have n elements. Yeah. And here, these numbers, actually, you can treat the numbers as the input data. Okay, input data. All right. Then we do comparison here. So our understanding, we have some simple understanding. Our understanding is, because the goal, we want to check if all the elements are distinct. Okay, check if all the elements are distinct, or because we need to check one by one, right? All the elements one after another, one by one. Or we can think in this way. For each element, we want to see if the current element is repeated somewhere in the array or not. Right? For each element, we do the check and see if it is repeated somewhere in the array. Right? So if you find one element that is repeated somewhere in the array, then you get the answer, right? Yeah. All right. So here, based on that understanding, first we check if the first element is repeated in the later part of the array. Yeah. So that's 0. Yeah. So we need to do n-1 comparison. N- means because we need to compare with the second, one by one, right? All the way, to the end. So we need to do n-1 comparisons. Okay, all right. Similarly, so the comparison result, if we do not find any match, not repeated, the first element is not repeated anywhere in the later part, then we need to check the second element. Okay. So then do the similar comparisons. We need an n-2 comparison and so on. Okay. In this way, so the second to last element, we need to do one comparison, but last one, we don't need to do any comparison. Okay. Yeah. All right. In this way, you can see for the worst case, right? For the worst case, we need to, do all the possible comparisons. Yeah. Yeah. If it's another worst case, we can stop somewhere in the middle, right? Yeah, because when you get a match, right? When you get a match, the function terminates immediately, and it returns false, right? Yeah, because not distinct. Okay, if it's distinct, then your function returns true. Yeah, the array contains distinct elements, true. Okay, otherwise, when you detect, so one element is duplicate somewhere, yeah, then you return false. Yeah. So the worst case, the number of comparisons. Yeah, you have best case and the worst case. Okay, the best case easy. When you do first comparison, yeah, you get a match. Yeah, so like this situation. Yeah, so the number of comparison is 1. Yeah. The worst case efficiency. Yeah, yeah. Think about the last 2 elements, the same. Yeah, all distinct. Yeah, that's also possible. Yeah. So you get this many, yeah. So that you need 1/2 times n minus 1. This many comparisons. Yeah. All right. Best case, worst case. All right. Yeah. The average case. So can you consider the average case? Yeah. Think about that, right? The average case. But the average case, if we want to do a good estimate on the average case, yeah, so the given information may not be sufficient. Yeah, so we need a little more information. Yeah. Otherwise, we cannot make good estimate. Yeah, because you need a probability. You need the probability data that the array contains distinct elements. What's that probability, right? So if you have the history data, you can use the history data to give you some estimate of the probability. Yeah. Then you can use that probability to do the weighted average. Remember, in our linear search, we use a probability P. So then our average, we use weighted average to calculate the average case efficiency. Yeah. Here we have the similar situation. Yeah. Yeah. But in this question, the probability is unknown. Okay. Yeah. So we cannot estimate average case well. Okay. At least, yeah, yeah. All right. Yeah. So that question, you can think about it. Okay. Yeah. Yeah. But you can think about it in this way: if the probability is given, okay, yeah, by the history data, we do statistics based on the history data. Yeah. So you get a probability estimate. Then you can think about how to calculate the average case efficiency in that situation. Okay? All right, think about that. Next, yeah. This time we want to do some preparation work, yeah, to organize the data. Yeah. But you need to pay some cost to organize the data. Yeah. So our method 2, we need to put some investment in data structure. Yeah. Mainly to organize the data with some friendly, yeah, more user-friendly data structure. Okay? All right. So let us sort the array first with certain cost. Yeah. Sorting actually pretty expensive. Yeah. The sorting process, yeah, usually quite expensive. Yeah. You need to pay a lot of cost. Yeah. All right. And here, when you do the sorting, yeah, I like to use a later result. Yeah. So this is the later result, n log n. Because at this point, we only learned one sort algorithm, selection sort. That is 1/2 n log n. Okay, 1/2 n times n minus 1. Yeah. But this number is not good. Okay. Later we have several other better sorts that can do better. Yeah. So we just pick one of those better sorts. Yeah. It gives the n log n efficiency. Okay? Yeah, n log n. Yeah. Here, let's assume we just use one of those better sorts. Yeah. Yeah. All right. That's our first step. We need an approximate. Yeah, here you can see that's approximate comparison number, n log n. Yeah. All right. Yeah. After that, now you can assume after this sorting step, preparation, sorting step, so you can assume the data is ordered. If the data is ordered, the next question, how to check if any element is repeated in an ordered array? Yeah. Can you do less work comparing with our method number 1, brute force method? So brute force 1, because the data is unordered. Okay? Here, imagine if the data is ordered. Can you save some comparison work when you do comparisons? Right? Yeah. Here, let's imagine we have our array is in the ascending order. Yeah. Ascending order. Yeah. Increasing order. Yeah. How to check if an element is repeated? Yeah, think about that. It's pretty easy. How to check if an element is repeated in an ordered array? Yeah. All right. Think about that. Okay. All right. Observation. Yeah. So because you need to understand your data well. Okay. Try to make your observation to discover some properties. Yeah. Properties. Yeah. So that's what you need to do when you understand this problem. Okay? All right. We only need to compare two adjacent elements. Think about it. This is a critical step. Yeah. Critical step. When you do your comparison, this time you only need to consider adjacent comparison. How about that? Okay? Yeah. Why is that? Because in an ordered array, if two elements have the same value, then you can imagine they should be in a block containing the same value, right? Yeah? So you will have a situation that you can find two adjacent elements with the same value. Okay? If two elements have the same value, so you can find two adjacent elements with the same value. Yeah? Because ordered. Okay? All the elements with the same value, they should be located back to back in a cluster of this array. Yeah, back to back locations. All right? Yeah. So you can find two adjacent elements with the same value. That's the critical observation. The critical property you need to discover. Okay. So that's a big improvement. Okay, big improvement. Yeah. Yeah. All right. So let's continue. Yeah. If we write a pseudocode to represent our algorithm, the main step is this for loop. Yeah. You just check compare two other JSON elements. Yeah. If true, true, because you find a repeated element not distinct, that's why your function returns false. Yeah. Yeah. If always return false. Yeah. If the condition never true, if you compare two other JSON elements, they never be the same. Okay? They never be the same, then at the end you return true because that's distinct. Okay? So that logic. In this way, you can count how many comparisons do we need. It's simple, yeah, because you only compare other JSON pairs. So how many comparisons do you need? Yeah. Can you answer this question quickly? Yeah. How many other JSON pairs can you find in this array? Yeah. Counting, simple counting question, right? Remember, I mentioned that counting by reference technique before, right? Can you apply that method, counting by reference, to answer this question quickly? Yeah. Each pair, you can associate it with another object that you can count easily. Okay? Yeah. The first pair, this pair, can you associate with this subscript? The second pair, can you associate with this subscript, and so on, right? Yeah. The last pair, can you associate with the last subscript, right? Yeah. So then you only count those subscripts used as the reference objects. Okay? Yeah. So your answer is n-1. Yeah. n-1 comparisons. Okay? Yeah? So you can see big improvement, right? Yeah. Big improvement. Yeah. Because if we compare with the previous one, 1/2 times n-1. Yeah. This step, you have a big improvement. But remember, you need to consider the first step. Okay? First step, you have n log n. Yeah. You need to combine the cost from both steps as the total cost of your method number 2. The title of part B, growth functions. Yeah. So this time, we will start to do some theoretical study. Yeah, theoretical study. Yeah. We need to study some abstract concepts. Yeah. The first abstract concept, that's the growth function. Okay. So what's that growth function? Yeah. All right. Formula between running time and the number of basic operations. Yeah. All right. So running time, we know, measure efficiency, and we also know it's not a stable measure. Yeah. And number of basic operation. Here we need to define this basic operation first. Yeah. All right. Yeah. Notations. Yeah. Yeah. So we assume the running time function T of n. Yeah. Capital T of n as the running time function. Yeah. All right. You can clock it and to see the value of this function. The function of number of basic operation. Yes. So here first we need to explain the meaning of this basic operation. Yeah. But if you count that number, so we use that C function, capital C function. Yeah. All right. This basic operation means the operation contributing the most to the total running time. Yeah. Yeah. All right. The contributing the most. Yeah. For example, in our polynomial problem, multiplication contribute the most. Okay, so we treat multiplication as the basic operation. Yeah. All right. Yeah. And in other problems, yeah. For example, the selection sort. Okay, selection sort. You have the comparison operation. You also have the assignment operation, right? Yeah, assignment operation. Yeah. But if you compare these two operations, you can see the comparison operation contributes the most. Yeah. Yeah. Because you need to do the comparison. Okay. Yeah. Even two elements have the same value, you need to do the comparison. Okay? Yeah. All right. Yeah, so here we want to study the relationship between these two functions, the capital T function and the capital C function. Yeah. Yeah, to study their relationship, so we need to make assumption. The execution time of basic operation. Yeah. So one basic operation on a particular machine. Yeah, because this little c op constant, usually it's different on different machines. Yeah. For a faster machine, this number smaller. Okay. On slower machines, so this number larger. Yeah. And so on. Okay, yeah, yeah. All right. So then, some approximate formula connecting these two functions. Yeah. So that is T of n, the total running time for the whole algorithm, approximately equals C op. Yeah. Little constant C op, okay, times the number of basic operations. Yeah. Yeah. Not exactly the same, but approximately the same. Okay? Yeah. All right. Yeah. So based on this formula, so then we want to study the algorithm efficiency. Yeah. So we want to find the appropriate way to study the algorithm, the efficiencies of the algorithm. Okay, yeah, all right. Yeah. All right, and the connection between these two functions. And we know counting number is a better measure, okay? Yeah. The time measure is not a good measure, right? Yeah, yeah, all right. And their relationship proportional with some constant. Yeah. All right. Yeah. Okay. Yeah. Then next, yeah, when we study, yeah, so here, yeah, remember our goal. Yeah. So here, so when we do this work, we need to clearly understand our goal. Yeah. Okay. So what we are doing here, the goal. Okay. All right. The high level study the efficiency of the algorithm. Okay. All right. Yeah. So that's the top level goal. Right. Yeah. But the top level goal. Although it's clear, right? Yeah, it's clear. Yeah. but not that concrete, not that specific. Yeah. So we need some specific objective. Okay, specific objective. Yeah, because study the efficiency, too vague. Okay, yeah, too vague. Yeah, yeah. We need something specific so we can grab. We can at least we know what to do next. Okay, what to do next, right? Yeah. All right. So here, let me go one more step further to, make our goal more specific. Okay. Yeah. So then that is the more specific goal or objective. That's classify the algorithms by their efficiencies. Okay, we want to classify. Okay, yeah, because there are so many algorithms out there, right? Distributed everywhere, and there is no good way to organize all these algorithms, right? Yeah. So we want to organize all the algorithms out there. Okay. Yeah. So the one important work people need to do, that is classify the algorithms by their efficiencies. Okay. Putting appropriate categories. Okay. Categories. Okay. So then the categories should be defined based on some properties of their efficiencies, based on certain properties of their efficiencies. Okay, yeah. So that's this goal or objective is more specific. Yeah. So we can, we can imagine, what kind of detailed work we need to do here. Yeah. All right. Yeah, so in order to do good classification, we need to do approximation. Okay, yeah. In the approach we take, ignore unnecessary details. Yeah, some details, because the impact of some details very small, very little. Okay, so we can ignore. Yeah. So in that way, yeah. So we try to group the algorithms, put the algorithms into different groups, okay, different categories. Yeah. All right. Then, regarding ignoring some less important terms, so one question is, because usually in our formulas we have many constants, so the question, how to deal with those constants in the formulas. Yeah. For example, in this formula there is this little c-op constant. Yeah. How do we deal with this little c-op constant? Okay. All right. Can we ignore some minor terms? Remember the dominant terms, major term, minor terms we mentioned before, right? Yeah. Dominant term. Yeah. So we need to keep the dominant term. Okay. Yeah. All right. So here we need to recall. Yeah. The dominant term and the minor term. Yeah. Here. So let me just review a little bit. Yeah. So the concept the dominant term and the minor term. So in one formula, we can identify the dominant term. Okay, versus, yeah, because other than the dominant terms, we may have many minor terms. Okay. The question, can we ignore the minor terms? Okay. All right. Ignore or not the minor terms. Okay. Yeah. Yeah. And last time, remember, I explained the meaning of dominant term, because how do you interpret the dominance, right? How do you determine the the term dominance? Yeah, because you need to have some representation for the dominance, right? Yeah. So our way to determine the dominance, yeah, so we use limit, calculus limit. The problem size n goes to infinity, yeah. Then the minor term, yeah. So let me use term minor, okay, over the term dominant, okay. This limit should be 0. That's the way we interpret dominance. Okay, when n goes to infinity, the ratio goes to 0. For that property, then we feel comfortable. We can say the denominator dominates the numerator, right? Yep, the denominator. Yep, infinity is 0. Then, based on this description, you can see we can comfortably ignore it, right? Yeah. Yeah. Because the limit is 0. Yeah. And we only consider the cases that n is very large. Yeah. For n not too large, then we don't worry. Okay. So because our computing power very powerful. Okay. Yeah. So we don't worry about n relatively small. Yeah. But when n is very large, even if our computing power is very strong, very powerful, we have limit, right? Yeah. Our computing resource and the power has some limit. Yeah. Yeah. So then, we may not handle large data well. Okay, so there is a chance we cannot handle large scale data efficiently. Yeah, that's our concern. Okay, all right. Yeah, so here the minor term we can ignore, right? Yeah, but for the constant, yeah, then it's a little complicated. So sometimes for some constant you can ignore, but for some constant, yeah, so you need to be very careful. Okay, yeah, you need to look at the location of those constant, right? Yeah, for example, let me show you the special location of the constant. So if let's say e to the c t, okay, this c is a constant. Then this constant you cannot ignore, right? Yeah, because when you change this constant from 1 to 2, it changes big. Yeah, the change is very big, right? Yeah. When you have a constant e to the t plus c, okay, then this constant you can ignore, right? Yeah. So you need to consider the location of your constant. Okay. Some places you can ignore, and some places you cannot ignore. Okay? Yeah. Yeah. All right. Yeah. Then another important observation we want to make is, let's look at the ratio. Yeah. T of 2n over T, capital T of n. Yeah. Yeah. Because when we take the ratio, you can see the little constant C op, little C op is gone. Okay. Yeah. So we simplify. Okay. Because when we first we know for these two functions, this particular ratio is the same. Yeah. The ratio here is we double the problem size. Okay. For each function, T function and a C function, we double the problem size. Then we take the ratio. Yeah. Of the problem size is doubled, what's the ratio of these two functions? You know, we can use this ratio to measure the value's increasing rate, right? Yeah. You know, the function is increasing with some rate, yeah, certain rate, okay, certain rate, yeah. And we can use this ratio to tell us every time when the problem size is doubled, the ratio of the function values, how large it is. Okay, the larger that ratio is, that the faster the function increases, right? Yeah. Yeah. So we get that information. Yeah, we get that information. Okay, it tells us sort of increasing rate information. Okay. Yeah. Yeah. So this is a, you know, some property, right? Yeah, a property we can observe. Yeah. All right. Yeah. Yeah. So based on this understanding, yeah, because this understanding also simplified the original formula a little bit, because this C constant is not important anymore. Yeah, because we cancel the C op, little C op constant. Yeah, so no matter its specific value is large or small, yeah, so we have this equal ratio formula, approximately equal. Yeah, this formula. Yeah. So we can. So how do we use this? How do we use this formula? We can use the formula to do characterization. Okay. Algorithm characterization. Okay. Yeah. Characterization. Okay. Yeah. All right. Introduce the growth function concept. Yeah. So what's the growth function? Growth, how fast it grows, right? Yeah, growth function. Yeah. How to define that growth function? Yeah. First, we need to know how to define a growth function. Yeah. Yeah. So we start from, yeah, so we do it from a few steps. First, we extract the major term from an efficiency function. First, you need to get efficiency function first, right? Yeah. So then you extract that major term. You have several terms. Yeah. The major term, yeah, that's the dominant term. Okay. Yeah. Minor, you know, non-major, minor, you know, non-dominant, minor, you know, dominant term. So let us use our selection sort as the example. Yeah. In this example, we know the efficiency function. Efficiency function is this one. This is the efficiency function. 1/2 times n minus 1. And we can expand this function here in two terms, right? Yeah. And the first term, dominant term, right? Or major term. The second term, minor term. Okay? Yeah. And you can see the dominance easily, right? Yeah. You can see the dominance easily. Yeah. Yeah. All right. View the dominant. Yeah. So how to see the dominance? You take ratio. Okay. Yeah. If you use dominant term over minor term, it's ratio infinity. Okay. Ratio infinity. The other way around, minor term over dominant ratio goes to 0. Yeah. All right. So this observation tells us the dominance. Okay. All right. But this dominant term contains a coefficient, 1/2 coefficient. Okay. 1/2 coefficient. All right. Here, yeah, because remember, hey, our goal, we want to define growth function. Yeah. So our goal here, define a growth function. Okay. Given this efficient function, from this efficient function, we want to extract its growth function from the original efficiency function, growth function. Okay. But growth function for some specific purpose, right? Yeah. What do you want to use the growth function? You need to have some specific objective using the growth function, right? Yeah. Okay. The growth function, it is used to characterize the algorithms. Right? That's the goal, objective. Okay? All right. But when you do the because your goal this time is the characterization, put in different categories, right? Yeah. So you need to define categories, right? Yeah. When you do characterize, what do you mean characterization? Okay? Characterize. You need to define appropriate categories, right? Okay. Categories. Category. All right? Yeah. Categories. Okay? Yeah. All right. So here you can see the growth function is used to define appropriate categories. Yeah. You need to understand this objective. Okay? Yeah. So when you select growth functions, yeah, so you just want to use it to define suitable categories. Yeah. All right. So here, when we select the growth in this example, when we determine growth functions, so we ignore the coefficient. Okay. So we simplify that dominant term 1/2 times n. We only extracted the n squared part. Yeah. We do not include the coefficient 1/2 coefficient. Yeah. Because in this way, if we ignore the constant, the leading constant part, we can make it simpler, right? We can make the function simpler. Yeah. And the relationship, this n squared and 1/2 times n squared, the relationship of these two expressions, their ratio is a constant. Okay, their ratio is a constant. Yeah. So here, if they have this, if their ratio is a constant, we put them in the same category. Okay. Yeah. Yeah. All right. So here you can see. Yeah. So let me write this. If the ratio of two functions is a positive constant. Okay. Yeah. So we put them in the same category. Okay. Same category. Okay. All right. Yeah. And this n squared is a simple form. This n squared is used as the representative of that category. Okay. Yeah, because it's so simple. Okay. Yeah. So this, it is used as a, good representative. Okay. Of the category. Okay. Okay. Yeah. Yeah. So here now you understand why people use the growth function, right? Do the characterization, and we want to use a simple expression in this category as the representative of the functions in this category. Okay. Yeah. So that's the the rationale to create this new concept, growth function concept. Okay. Yeah. All right. Yeah. So that's the reason, here we call this special function the growth function special. Okay. All right. Yeah. Next. Yeah. So after that section, we understand the concept, growth function concept. Okay. All right. Next, we want to compare growth functions. Now, we assume, we have two different growth functions. Yeah. So now we want to do comparison. Yeah. Which growth function grows faster? Which growth function grows slower? Yeah. So we want to see that. Yeah. So in this section, we need to do calculation to see which one grows faster. Yeah. So let us just use the two growth functions from our problem number 5, the element uniqueness problem. Yeah. Yeah. So we have two solutions, right? Two methods, method 1 and method 2. Yeah. Each method, we can find the growth function. Yeah. Then we do comparison. All right? Yeah. Which method is better? From method 1, we have a worst case efficiency function, and method 2 we have a worst case efficiency function. Yeah. And from each efficiency function we can extract its growth function. Yeah. So the first one, we extract n squared as its growth function. For the second efficiency function, we can extract its growth function n log n. Okay, yeah. So when we compare these two efficiency functions, yeah. So now we want to compare these two efficiency. That's equivalent to compare their corresponding growth functions. Yeah, because the first growth function belongs to the first category. Okay, yeah, belongs to the first category. The second growth function belongs to the second category. Okay. Yeah, and its growth function is used as a representative of the first category. Okay, then the second growth function is used as the representative of the second category. Okay, yeah. Now we just compare these two representatives. Okay, yeah, yeah. How to compare? We take the ratio. Yeah, take the ratio and calculate the limit of the ratio. Yeah. So this time we calculate this limit. Yeah. When n goes to infinity, n squared over n log n. Okay. Yeah. How to calculate this limit? Yeah. First, we do simplification. Yeah. Cancel the common factor. Yeah. Yeah. After simplification, we need to calculate the limit when n approaches infinity, n over log n. How to calculate this limit? Okay, yeah, yeah. So you need to recall in calculus, how do you calculate this limit? Okay, yeah, all right. Yeah, here this log n, yeah, because we do not specify the log base, right? Yeah, we do not specify. Yeah, because sometimes the base number is not that important, so we ignore it. Yeah. All right. So if you want to, but in calculation we may need to use the base. Yeah. Here we use a, appropriate base A. Yeah, we choose appropriate base A, and this A should be a real number greater than 1. Okay, greater than 1. Yeah. Yeah. Because if A less than 1, then the log function is a negative function, right? Yeah. And we know our efficiency function should be a positive function. Yeah. So for that reason, so we assume A should be a constant that is greater than 1. Yeah. All right. Next question. Can you see this limit goes to infinity? Yeah. Do you have the knowledge, information to tell you this limit should be infinity? Yeah. N over log n. Okay. Yeah. For some of you, it may not be that obvious, right? Yeah. For some of you, it may not be that obvious. Why? Because we know each term goes to infinity. N goes to infinity, and this log of n function also goes to infinity, right? Yeah. Yeah. How do you know that infinity over infinity also goes to infinity, right? Yeah. So you need to convince people. Yeah. You need to convince people that. Yeah. Yeah. All right. Yeah. So here we need to do some work. Yeah. To compare. Yeah. Yeah. So there are a few methods we can use. The first method, yeah, we do variable substitution. Yeah. And the reason is many people, they do not feel very comfortable on logarithm function. Yeah. Some people, they do not have a good idea, how large is a log function. Yeah. 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 So for that reason, yeah, if you do not feel very familiar with the log function, So we want to get around it. Yeah. We want to avoid it. We want to do some variable substitution to eliminate the logarithm function. Yeah. To do that, we introduce a new variable, we call it u variable, equals log base a of n. Yeah. After this new variable is introduced, by the definition of the logarithm, we can have this n equals a to the u. N. Yeah. A is a constant greater than 1. So a equals a to the u. Yeah. Then, if we go back to the original ratio, the limit, yeah, after substitution, yeah, we have this new limit expression. U goes to infinity, then the numerator function becomes a to the u, and denominator function becomes u. Yeah. All right. Yeah. So the same limit in different forms. And in the new form, the logarithm function is gone. Okay? You do not see the log function. Okay? You do not see the log function. Okay? Yeah. So you have the ratio of an exponential, a to the u, it's an exponential function, over that simple u function. U is a linear function. So you have a ratio that is an exponential function over a linear function. Okay? All right. Can you see it should be infinity, an exponential function with base greater than 1, okay, over a linear function. Yeah. Yeah. Here, yeah, if you know, so this fact, an exponential function dominates any polynomial. Yeah. Because linear function is a special polynomial. An exponential function can dominate any polynomial. Okay? Yeah. So that's people always use in the real world, real life. Yeah. Yeah. So many people say, exponential function grows much faster than any polynomial function. Yeah. But yeah, although that's some basic fact people use in everyday life, yeah. But if you want to see the justification, right? Yeah, because some students may want to know why, right? Yeah. So yeah. So we can prove it. Yeah. We can prove it. Okay? We can show, by rigorous math proof, this limit must be infinity. Okay? All right. Yeah. So then, the last step, we need to prove it. Yeah. We need to calculate the limit and to see it is infinity. Yeah. To do it, we need to apply a special calculus method called the L'Hopital's rule. Yeah. Look at this, L'Hopital's rule. In calculus 2. In calculus 2, this topic is in calculus 2, not calculus 1. Calculus 1, you do not learn L'Hopital's rule. Yeah. Calculus 2, yeah. So you learn this L'Hopital's rule. Yeah. All right. Yeah. Let me leave this topic next time. Okay? Yeah. Yeah. Because we need to spend at least 10-something minutes, yeah, to complete this L'Hopital's rule. Okay, I need to explain this L'Hopital's rule. Yeah, review a little bit. All right. Yeah. All right. So let's stop right here. This is our last slide of part B. Okay. So the next time we finish this last slide, then we start part C. Part C. Okay. All right. Yeah.